There are moments in the history of the Earth when the planet feels less like a world of rock and water, and more like a living memory written in fire, ocean, and time. The Archean is one of those moments. A world without continents as we know them, without oxygen, without life as we understand it, yet already carrying every future possibility in its silent depths. To explore this era is to step into a chapter of the cosmos where everything was raw, unstable, and astonishingly full of potential. And here at Chronicles of Earth, we believe that understanding this ancient world reveals who we are in the universe. This is the place where the first oceans found their rhythm, where minerals forged the chemistry of life, and where sunlight touched the planet in a way that would change everything. If you've ever wondered how humanity's story truly begins, you're standing at the doorway right now. But before we cross it, let me leave you with our channel's signature call. Every era leaves a mark. Every mark tells a truth. This is the heart of Chronicles of Earth. What you're about to see will challenge your assumptions about the planet, about life, and about how fragile and extraordinary our place in the cosmos truly is. Some scientists call the Archean the cradle of possibility. Others see it as the universe's boldest experiment. I invite you to decide for yourself. If you're ready to journey through fire, oceans, and 4 billion years of transformation, then make sure you subscribe to Chronicles of Earth. Activate notifications and join a community that seeks not just information, but understanding. The rise of the first stable rocks and the birth of the oceans. The Archean begins in silence, as if the planet were taking its first deep breath after surviving the inferno of its youth. What once was a molten sphere is now cooling enough to form the earliest fragments of solid ground, giving Earth its first sense of permanence. These newborn rocks rise and sink, reshaped constantly by heat and pressure, yet determined to endure. The history of the Earth quietly shifts as these foundations settle into place. And through them, the story of every future mountain, continent, and ocean begins. Beneath the planet's dark skies, volcanic arcs rise like glowing scars, marking the restless boundaries of this young world. Islands of primitive crust drift across a churning global ocean of magma, freezing and melting in repeated cycles. With each turn, crystals lock together, forming the first stable continental fragments known as cratons. They are the ancient memory keepers of our geological eras, still surviving today in places like Canada, Australia, and Africa. These rocks whisper the earliest chapters of Earth's long journey through the cosmos. As the surface stabilizes, temperatures finally fall enough for vapor to condense again and again, forming rains that last for centuries. The raw heat of the planet turns each raindrop to steam, but the sky does not relent. Over thousands of years, the balance shifts, and liquid water starts to win. Vast tides gather in low basins carved by tectonic forces, giving birth to the first true oceans. And with their arrival, the planet softens, turning from a world of fire into a world of water. These early oceans are nothing like the sapphire expanses we know today. They are thick with dissolved minerals, almost black under the faint sunlight that reaches them. Yet their presence marks a turning point in the origin of life, because water becomes the stage on which chemistry will someday awaken. The Earth cools further, allowing these oceans to deepen and widen, wrapping the planet in a shimmering, restless skin. Here, the planet transforms from chaotic to dynamic, from violent to fertile. The future of life begins quietly beneath these shimmering waves. Above the oceans, Earth's earliest crust anchors itself with growing confidence. While volcanic eruptions continue to shape the landscape, fragments of proto-continents strengthen, resisting the pull of tectonic destruction. Through intense cycles of metamorphism, these ancient rocks turn into time capsules, preserving minerals older than any biological existence. They teach us that stability is not the absence of change, but the endurance of form through relentless transformation. And in this era, resilience becomes Earth's defining feature. As tectonic plates slowly guide these first continents across the planet, they collide, break apart, and drift again in a constant ballet of creation. Each collision releases heat, forms mountains, and reshapes coastlines, enriching the oceans with minerals essential for future life. The planet's surface becomes a living engine of renewal, driven by forces deep within the mantle. These geological movements weave Earth into a world capable of complexity. And although humanity is billions of years away, our story is already written into this shifting crust. With oceans in place, sunlight begins to interact with the water's surface, triggering delicate reactions that will later support the earliest ecosystems. The interplay of light, water, and heat produces gradients and chemical patterns across the planet. It is here that the stage is set for the emergence of life, long before bacteria or cyanobacteria appear. Earth becomes a world not yet alive, but undeniably ready for life. The cosmos watches as our planet prepares for its next great leap. By the end of this first great chapter of the Archean, Earth has transformed from a fiery sphere into a stable, water-covered globe rich in potential. Its rocks anchor memory, its oceans cradle possibility, and its atmosphere becomes a thin veil waiting to be rewritten by biology. Everything that humanity will someday study, question, and marvel at begins here. This is where the planet earns its place among the worlds capable of life, and every future journey, scientific or personal, traces back to this moment of profound transformation. The emergence of the first microscopic life, ancient bacteria awaken life, begins not with thunder, but with a whisper hidden in the darkness of the ancient oceans. As Earth stabilizes, chemical reactions unfold across mineral-rich seafloors, driven by heat rising from beneath the crust. In this world shaped by extreme events, simple molecules gather, break, and reorganize endlessly. Somewhere within this restless chemistry, the first self-replicating structures form, fragile yet persistent. With them, the history of the Earth enters a new and irreversible phase. These early life forms are bacteria, tiny, invisible architects of a future they cannot imagine. They do not swim with purpose or sense their environment with intention, yet their presence marks the beginning of biological time, a shift from pure geology to the first pulse of life. Supported by the energy gradients near hydrothermal vents, they multiply slowly at first. Each replication, each mutation, becomes a small step toward the complexity humanity will one day inherit. In their simplicity, they carry the weight of every future species. The oceans become laboratories of the universe, where bacteria forge alliances with minerals, metals, and water. They feed on chemical energy released from the planet's interior, adapting to temperatures and pressures modern life could hardly survive. Through their metabolic cycles, they begin altering the chemistry of Earth itself. They consume, transform, and release, turning raw elements into biological patterns. Without intention, they become the first engineers of the planet. As these microscopic pioneers thrive, they gradually spread across Earth's oceans, colonizing environments once thought uninhabitable. The deep-sea vents, the mineral crusts, the volcanic shores, all become stages for their expansion. Each environment shapes their evolution, pressing them toward new metabolic possibilities. They are small but countless, forming unseen kingdoms beneath the waves. Through them, the planet shifts from a passive world to an active, living system. These bacterial communities form mats and films across mineral surfaces, stabilizing their tiny ecosystems. In doing so, they create vast microbial landscapes stretching for kilometers, shimmering beneath the early sunlight. Though humanity will never witness these scenes, their impact echoes across every geological era. They show us that life does not require complexity to transform a planet. It only requires persistence and time. Over millions of years, these bacteria refine the ancient balance between chemistry and biology. Their metabolic reactions start shaping the oceans, cycling essential elements and creating gradients that support even more diversity. What begins as an isolated spark becomes a global presence. They mold the Earth slowly, patiently, one replication at a time. And with every generation, they prepare the world for breakthroughs still far in the future. Hydrothermal vents remain crucial in this chapter, acting as thermal engines that feed and protect early life. Around them, towering mineral chimneys rise, releasing heated water rich in metals and nutrients. Bacterial colonies cluster in these oases, shielded from harsh surface conditions. These early ecosystems offer a glimpse into the fundamental rules of life on Earth. They also remind us that life can arise in places most of the cosmos would consider impossible. By the end of this phase, bacteria dominate the oceans completely, establishing themselves as the true foundation of the planet. They are silent but unstoppable, guiding Earth toward its next monumental transformation, the birth of photosynthesis through cyanobacteria. The story of humanity, of the planet, and of the universe's patience is hidden within their microscopic simplicity. Life has begun, and nothing will ever return to the stillness that came before. Cyanobacteria and the dawn of photosynthesis. As Earth drifts through the cosmos, a quiet revolution begins in the ancient oceans. Among the thriving bacterial communities, a new lineage emerges with a remarkable ability. Cyanobacteria, capable of capturing sunlight and turning it into chemical energy. This moment marks one of the most profound transitions in the history of the Earth. For the first time, life learns to harvest light, rewriting the rules of survival on a planet shaped by darkness and fire. The world will never be the same again. Cyanobacteria do not claim the spotlight through size or speed, but through chemistry. Their internal structures host pigments that absorb sunlight, allowing them to perform photosynthesis, a process that transforms the universe's most abundant energy source into life's currency. With each photon they capture, they produce oxygen as a byproduct, releasing it into the ancient seas. This subtle shift sets the stage for the future atmosphere, and in their quiet persistence, they become Earth's first true global influencers. These microorganisms gather in vast colonies, forming structures known as stromatolites, layered towers of life and sediment. Over millions of years, these formations grow in shallow waters, rising like organic monuments beneath the early sunlight. Their presence records the slow but powerful march of biological time. Today, some of the oldest surviving stromatolites can still be found in places like Shark Bay, Australia, acting as windows into the planet's distant past. They are living archives of Earth's earliest ecosystems. As cyanobacteria multiply, sunlight becomes the dominant force shaping the young biosphere. What begins as a local chemical trick becomes a planetary phenomenon, reshaping the oceans and the atmosphere one molecule at a time. These organisms convert carbon dioxide into biological matter, slowly altering the chemical balance of the seas. This shift begins influencing climate patterns, energy flows, and ocean chemistry. The foundations of a future complex biosphere are being laid beneath the waves. The release of oxygen into the oceans creates new pathways for evolution. At first, oxygen reacts with dissolved iron, forming vast layers of rust-colored minerals on the ocean floor. These deposits, known as banded iron formations, are among the most significant geological archives of early Earth. They signal the beginning of the Great Oxidation process, a multi-million-year transformation that will eventually reshape the atmosphere. Cyanobacteria unknowingly set this chain reaction in motion. With oxygen slowly accumulating in the water, new biological opportunities begin emerging. While most early life struggles under the toxic effects of free oxygen, some lineages adapt, building metabolic strategies that use oxygen for energy. This adaptation marks the first small steps toward the complex metabolisms that will define later life forms. It demonstrates that evolution is not a sudden leap, but a patient dialogue between environment and biology. Cyanobacteria ignite that dialogue with every cycle of photosynthesis. The spread of cyanobacteria becomes global, turning Earth into a world driven by sunlight rather than the heat of hydrothermal vents alone. Their photosynthetic activity expands across coastlines, shallow seas, and open waters, establishing the first planetary-scale biological system. In doing so, they create conditions that will eventually allow multicellular organisms to arise. They are the quiet architects of complexity, shaping the blueprint of life long before any creature develops eyes to witness the sun. By the end of this chapter, cyanobacteria have transformed Earth into a chemically evolving planet, preparing it for the great oxidation event still to come. They demonstrate that even the smallest forms of life can wield power on a cosmic scale, altering oceans, atmosphere, and climate. Through them, the planet shifts from a dark world to one illuminated by the chemistry of light. Their legacy echoes through every modern ecosystem, reminding humanity that life's greatest revolutions often begin in silence. The first accumulation of oxygen in Earth's atmosphere. The rise of oxygen begins as a slow, almost invisible shift, whispered through the ancient oceans long before the sky feels its touch. Cyanobacteria continue releasing oxygen through photosynthesis, but the early atmosphere absorbs none of it at first. Instead, oxygen reacts instantly with iron, sulfur, and volcanic gases, disappearing into chemical traps across the planet. Yet with each passing millennium, these traps fill, saturating the oceans with oxidized minerals. Only then does oxygen begin its steady climb toward the air above. As these chemical reservoirs reach their limits, free oxygen finally escapes into the atmosphere in small, fragile quantities. The sky remains a veil of methane and nitrogen, tinted in muted tones by volcanic particles drifting through the air. But dissolved oxygen from the ocean starts rising, pushing against the planet's boundaries like a tide preparing to break. This change is subtle, but it marks one of the most significant turning points in the history of the Earth. The atmosphere is on the edge of transformation. The introduction of oxygen brings both opportunity and crisis. For many ancient microbes that evolved in oxygen-free environments, this new gas is lethal, disrupting the chemistry they depend on. Entire ecosystems collapse as oxygen accumulates. Yet in the same moment, new metabolic pathways emerge in other microorganisms, allowing them to harness this potent molecule for energy. The planet becomes a battleground of adaptation, innovation, and survival. Evolution marches forward through both loss and potential. As the atmosphere absorbs more oxygen, chemical reactions paint the planet with new colors. Iron-rich waters rust and settle into layers across the seafloor, creating banded iron formations that future geologists will study to decode Earth's early story. The oceans shift from dark tones to clearer hues as oxygen purifies and redefines them. This chemical shift reshapes the climate, altering how heat moves between the ocean and the sky. Earth becomes a world increasingly influenced by biological processes rather than pure geology. The arrival of oxygen initiates the slow fading of methane, one of the planet's most powerful greenhouse gases. With methane decreasing, Earth's climate cools, triggering potential ice expansions and altering global temperatures. The planet enters a delicate balance, guided by the interplay between life and atmospheric chemistry. For the first time, living organisms influence the planet's future climate, and through this balance, Earth becomes capable of supporting more diverse life in the ages to come. Over millions of years, oxygen continues rising, though still far below modern levels. Thunderstorms, ultraviolet radiation, and volcanic activity interact with this new element, forming ozone in the upper atmosphere. This thin layer becomes a protective shield, absorbing harmful ultraviolet radiation from the cosmos. Without it, life could never safely expand beyond the depths of the oceans. Oxygen, once a dangerous pollutant to early life, becomes the guardian of all future ecosystems. As atmospheric oxygen slowly spreads, the sky brightens and becomes more stable. The dynamics of weather shift, wind patterns evolve, and the global climate begins to stabilize. These changes create new environmental spaces where life can flourish. The planet transitions from a world dominated by chemical and volcanic processes to one shaped by biology. This shift marks the beginning of a new chapter in geological eras, where life and planet evolve together. By the end of this transformative phase, Earth stands on the threshold of the Great Oxidation Event, a dramatic surge that will redefine atmosphere, climate, and biology forever. Oxygen becomes the invisible thread that ties together the future of life, from bacteria to humanity. It is the molecule that will someday fill our lungs, ignite fires, shape evolution, and anchor ecosystems. And it all begins here, with a patient, steady rise that changes the destiny of the entire planet, the early cooling of the planet and the stabilization of its surface. As the Archean world continues to evolve, Earth slowly releases the heat trapped from its violent birth. The planet cools not in a single moment, but across millions of quiet, persistent years. Volcanic eruptions remain constant, yet their intensity gradually softens as the mantle settles. This cooling transforms the crust, allowing the first true continents to take shape beyond brief volcanic islands. The history of the Earth shifts from a world of chaos to a world learning to balance itself. With each passing millennium, the planet's internal heat diminishes enough to provide long periods of geological calm. Magma flows become slower, and tectonic movements begin to follow more predictable patterns. These early stabilization cycles allow continental fragments to strengthen, resisting the constant recycling of the crust. In this new equilibrium, the planet becomes more than a battlefield of fire and stone. It becomes a stage capable of supporting sustained oceans, climate patterns, and eventually, life. As heat escapes into space, the planet's surface behaves less like a molten ocean and more like a dynamic shell. The cooling crust thickens, creating zones of rigidity that anchor the earliest tectonic plates. These plates begin interacting in ways that mirror modern Earth, colliding, subducting, and shaping primitive landscapes. With each collision, mountains rise and erode, returning minerals to the sea. The cycles of destruction and renewal become essential rhythms in the planet's evolution. The cooling also affects Earth's atmosphere. Reduced volcanic outgassing stabilizes gas compositions, allowing the early climate to settle into patterns shaped by sunlight and ocean interactions. Thick clouds, once powered by extreme temperatures, become more predictable in movement and form. Rainfall turns from violent torrents into more consistent cycles, feeding the oceans and shaping coastlines. Through these changes, the planet's climate begins to resemble a system capable of long-term biological stability. Within this increasingly stable environment, oceans deepen and expand, becoming reservoirs of mineral-rich water. Their surfaces reflect faint, early sunlight, creating the first climate-regulating feedback loops. Evaporation, cloud formation, and rainfall begin to shape global patterns, redistributing heat around the planet. These systems create pockets of environmental stability that will later support the rise of microbial diversity. The stage for life grows broader and more inviting with each climatic shift. The cooling of the mantle also slows the frequency of massive volcanic resurfacing events. Instead of constantly burying early oceans and continents beneath new lava, eruptions now occur in cycles more similar to modern geological patterns. This allows rock layers to accumulate and record Earth's early story. Sediments settle into basins, forming archives of minerals that track temperature changes, volcanic activity, and atmospheric shifts. Through these layers, scientists today decode the timeline of Earth's long evolution. As continental fragments strengthen, they begin resisting subduction, allowing them to grow and assemble into larger land masses. These early continents drift across the oceans like ancient rafts, shaped by tectonic forces below. Their movement regulates ocean circulation, creating varied environments across the planet. The interaction between land, sea, and atmosphere becomes increasingly complex, mirroring processes that will dominate future geological eras. Cooling transforms Earth into a world governed by systems, not just raw energy. By the end of this stage, Earth stands in a delicate balance between heat and stability. The crust is strong enough to resist constant destruction, yet active enough to keep shaping oceans and continents. The climate becomes more predictable, oceans more enduring, and the atmosphere more responsive to biological influence. Through cooling, Earth discovers its rhythm, a rhythm that will support life, evolution, and eventually humanity. The planet becomes not just a sphere of rock, but a living world in motion. The formation of the primitive crust. Earth's earliest continents take shape. In the deep silence of the Archean world, the formation of the primitive crust unfolds like a slow, deliberate act of creation. Beneath the oceans, molten rock rises from the mantle, cooling into rigid plates capable of drifting and reshaping the planet. These first crustal fragments are fragile, constantly recycled by heat and tectonic pressure, yet determined enough to persist. Their survival marks a turning point in the history of the Earth. Through them, the planet gains its first permanent surfaces. As tectonic forces push and pull, pieces of this young crust collide and weld together, forming the earliest continental nuclei known as cratons. These cratons are small at first, mere seeds of what will someday become vast continents. Built from minerals forged under extreme heat, they resist erosion better than any other early rock. Their resilience allows them to endure billions of years of geological change. Even today, their ancient cores anchor some of the oldest landscapes on the planet. The formation of the primitive crust is not a gentle process. Volcanic arcs erupt across the planet, forcing lava to rise, cool and solidify into new land. Underwater eruptions add fresh layers to the seafloor, while above, volcanic islands rise and collapse in endless cycles. These bursts of creation generate the raw material for continental growth. In this chaotic interplay, the Earth begins to shift from a world of temporary surfaces to one with lasting geological identity. As crustal fragments stabilize, they begin interacting through mechanisms that resemble modern plate tectonics. Subduction zones form where heavier oceanic plates dive beneath lighter continental material. These deep trenches create regions where new minerals form, driving chemical diversity across the crust. The interactions produce heat, pressure, and metamorphic transformations that further strengthen continental roots. Through this cycle, the planet's geological eras gain structure and momentum. Over millions of years, early continents grow thicker and broader, resisting the mantle's heat long enough to preserve their form. Their surfaces record impacts, volcanic flows, and oceanic deposits, creating layered archives of Earth's early environment. These rock layers become clues scientists use today to decipher extreme events from the distant past. They show that Earth's crust was not static, but constantly responding to forces from within and from the universe above. As these continental seeds expand, they reshape the planet's climate and ocean chemistry. Their presence alters ocean circulation patterns, forcing waters to move around them in new ways. This flow redistributes heat, minerals, and nutrients, influencing environments where early life thrives. The interaction between land and sea becomes a powerful engine of change, guiding the direction of evolution. Without continents, life's future pathways would have been entirely different. The stabilization of the primitive crust also influences the atmosphere. Larger continental surfaces absorb sunlight differently than vast oceans, shaping temperature gradients and wind patterns. Volcanic activity along continental margins releases gases that mix with the changing atmosphere, contributing to climate regulation. Through each shift, Earth becomes increasingly sensitive to biological and geological feedbacks. This sensitivity sets the stage for future transformations, including the rise of oxygen. By the end of this chapter, the planet stands as a world of emerging continents drifting across deep oceans. The primitive crust forms the backbone of Earth's long-term stability, anchoring the world through billions of years of change. It provides the first stable landscapes where life will eventually expand beyond water. And with every tectonic collision, volcanic eruption, and cooling cycle, the planet becomes more dynamic, more complex, and more capable of sustaining the universe's rarest phenomenon, life. The late heavy bombardment and its lingering aftermath. Even as Earth's surface stabilizes and continents begin to take shape, the sky above remains a place of danger. The late heavy bombardment, a period of intense asteroid and comet impacts, still echoes into the early Archean. Though the peak has passed, debris from the young solar system continues striking the planet with unpredictable force. Each collision reshapes landscapes, vaporizes oceans, and injects minerals into the atmosphere. The history of the Earth carries these scars as reminders of its cosmic vulnerability. Some impacts are small, leaving only brief disturbances in the oceans or shallow craters on fragile crust. Others unleash devastation powerful enough to melt large regions of the surface. These colossal collisions disrupt the early climate, triggering short-term heating or cooling, depending on the size and composition of the incoming object. Through every strike, the relationship between Earth and the cosmos deepens. The planet learns resilience not through calm, but through survival. Despite their destructive nature, these impacts deliver chemical riches essential for life. Meteorites bring complex organic molecules and elements forged in distant stars, adding to Earth's growing chemical inventory. Some scientists believe these deliveries helped accelerate the origin of life by enriching the oceans with carbon, nitrogen, and key minerals. Whatever their exact role, the evidence is clear. Cosmic events shape the direction of Earth's evolution. Extreme events are woven into the fabric of our planet's story. As impacts continue, the oceans absorb massive waves of heat and dissolved minerals. Hydrothermal systems expand across the seafloor, feeding microbial ecosystems that find refuge in extreme environments. Each shock to the crust opens new vents and fractures, creating fresh habitats for early bacteria. Life, though fragile, adapts to every shift. In this era, survival favors the smallest organisms with the greatest flexibility, setting the stage for biological innovation. The craters formed by these collisions become geological vaults, storing evidence of ancient catastrophes. Over time, erosion and tectonics erase many of them, but traces remain in the deep layers of continental crust. Scientists today read these clues like pages from an ancient cosmic journal. They tell us that Earth's early history was not peaceful, but punctuated by frequent moments of violent transformation. And through each moment, the planet continued moving toward complexity. Volcanism increases in response to large impacts, as energy from collisions destabilizes sections of the mantle. Lava floods reshape coastlines, expanding land in some regions while burying others under molten rock. These eruptions release gases into the atmosphere, influencing climate and ocean chemistry. Yet amid the chaos, stability gradually strengthens. The Earth absorbs each blow and slowly rebuilds, fueled by deep internal processes that counterbalance the destruction from above. As the solar system becomes more orderly, the frequency of major impacts decreases. The planet enters a slower, more predictable rhythm of cosmic encounters. This shift allows biological and geological systems to develop without constant interruption. Oceans settle into long-term cycles, continents expand, and atmospheric chemistry evolves toward greater balance. Earth's transformation from a vulnerable young world into a resilient, life-supporting planet accelerates. By the end of this period, the lingering aftermath of the late heavy bombardment has reshaped Earth into a chemically enriched and geologically dynamic world. Its scars become ingredients for progress. Its trauma becomes opportunity. The planet stands stronger, more stable and more capable of supporting the emergence of new life forms. In this era, Earth discovers that survival is not merely endurance, but adaptation to the cosmos itself. The first signs of water, the oceans deepen and transform the planet. As the planet cools and stabilizes, the first undeniable signs of long-lasting water begin to appear across Earth's surface. What began as vapor collapsing into rain now becomes continuous, global cycles of evaporation and condensation. For thousands of years, storms circle the world, carving channels, filling basins and sculpting new landscapes. Each drop of water carries the story of the cosmos, shaped by volcanic heat and atmospheric chemistry. The history of the Earth turns a new page, written in liquid form. With the crust thickening, ocean basins become more capable of holding vast quantities of water. Rainfall no longer evaporates immediately upon touching hot rock. Instead, it gathers in growing pools, merges into larger bodies and ultimately forms the early oceans. These oceans are murky and mineral-rich, their surfaces reflecting volcanic skies. Yet beneath their chemical density lies the foundation for all future biological evolution. Water becomes Earth's most transformative force. As oceans expand, they begin to regulate temperature by absorbing heat during the day and releasing it slowly at night. This stabilizing effect marks one of the earliest climate control systems on the planet. The existence of long-term liquid water begins influencing everything: tectonic cycles, atmospheric chemistry, and early ecosystems. For the first time, Earth behaves like a planet with interconnected systems rather than isolated geological events. Water binds these systems together. The presence of oceans changes the texture of Earth's atmosphere. Evaporated water forms clouds that travel long distances before releasing rain elsewhere. These movements distribute heat, shaping early weather patterns that guide the planet toward long-term stability. Even without modern continents or advanced landscapes, the climate begins forming recognizable cycles. Through these rhythms, ocean and atmosphere become partners in the construction of the planet's identity. Within the oceans themselves, the chemistry becomes increasingly complex. Minerals dissolve into the water, creating environments rich in sulfur, iron, and trace elements essential for microbial life. These elements interact with early bacteria, fueling metabolic pathways that will define the origin of life. Hydrothermal vents thrive under thicker ocean pressure, supporting colonies that expand outward into new territories. Water becomes both cradle and catalyst. As the oceans deepen, tides generated by the moon influence their movement, carving early coastlines and stirring nutrient-rich waters. Though Earth rotates faster than it does today, these tides still create essential mixing patterns that feed microbial communities. The interplay of gravity, rotation, and water creates predictable rhythms that life will someday depend on. Through these cycles, Earth becomes a world ruled not only by geology but by motion. The expansion of water across the surface also alters the reflectivity of the planet. Oceans absorb sunlight differently than rock, changing the distribution of heat around Earth. These shifts influence atmospheric circulation and help create thermal gradients necessary for emerging weather systems. With each adjustment, the planet becomes more balanced, more dynamic, and more capable of sustaining diverse environments. Water shapes the future in every direction. By the end of this early chapter, oceans cover most of the planet, forming a global canvas on which life will continue to evolve. Their presence stabilizes the climate, drives chemical reactions, and defines Earth's relationship with the universe. These first signs of water mark not just a milestone in geological eras, but the beginning of every biological possibility. From this moment on, water becomes the thread connecting the birth of the planet to the rise of humanity. Gravitational stabilization and the refinement of Earth's rotation. As oceans spread and continents strengthen, Earth enters a period where its rotation and gravitational balance begin to settle into a long-term rhythm. These changes unfold quietly, driven by interactions between the planet's mass, its molten core, and the gravitational pull of the moon. In the early Archean, Earth spins faster than it does today, completing a full rotation in roughly 14 to 16 hours. This rapid spin shapes tides, winds, and ocean circulation, imprinting motion into every corner of the planet. The history of the Earth becomes a story not only of matter but of movement. The moon plays a central role in this transformation. Having formed from a colossal impact early in Earth's life, it still orbits closer to the planet than it does today. Its gravitational pull generates strong tides that stir the oceans with remarkable intensity. These tides slow Earth's rotation gradually, creating friction that warms the oceans and crust. This slow deceleration shapes the length of the day, influencing everything from climate stability to the conditions required for the origin of life. Through these forces, Earth and Moon evolve together. As Earth's rotation slows, the atmosphere responds with shifting wind patterns. Faster rotation once drove violent global storms, but with time these storms soften, allowing more stable weather systems to form. This stabilization affects temperature distribution, shaping early climate zones, even in a world without large, modern continents. Atmospheric motion becomes increasingly predictable, providing a more supportive environment for early ecosystems. The universe teaches the planet that balance emerges through gradual motion. The gravitational relationship between Earth and the Moon also stabilizes Earth's axial tilt. Without this influence, the tilt could swing wildly, creating chaotic seasons and climate extremes. Instead, the Moon anchors Earth's orientation, ensuring long-term consistency in how sunlight falls across the globe. This stability becomes one of the most important factors in the planet's ability to support life over billions of years. It keeps Earth's climate within a range that allows oceans to persist and ecosystems to grow. Earth's molten outer core contributes to this stabilizing process as well. Its constant motion generates the planet's magnetic field, which acts as a shield against harmful solar radiation. Although weaker in the Archean than it is today, this field prevents the solar wind from stripping away Earth's developing atmosphere. Rotation influences the dynamo effect within the core, making the magnetic field's existence tied directly to the length of Earth's day. Through this connection, gravity, rotation, and magnetism work as a unified system. With gravitational forces aligning and rotation slowing, tides begin shaping the structure of early coastlines. They carve channels, stir sediments, and create nutrient flow patterns that help sustain microbial life. These tidal influences also refresh shallow waters, preventing stagnation and encouraging chemical diversity. In this way, the Moon's presence becomes a silent partner in the early evolution of life. Without it, many essential environmental cycles would never have taken shape. As rotation continues gradually slowing, days lengthen, and the rhythm of sunlight changes. Longer daylight hours allow more time for photosynthetic organisms like cyanobacteria to collect energy. This increased exposure accelerates the production of oxygen, influencing atmospheric development over millions of years. Earth's rotation becomes not just a physical characteristic, but a biological driver woven into the fabric of evolution. Through it, the planet's connection to the universe deepens. By the end of this phase, Earth's gravitational and rotational systems establish the stability required for future life to thrive. The planet turns with a steadier rhythm, its tilt anchored, its tides moderated, and its climate supported by predictable cycles. Rotation, gravity, and celestial partnership shape Earth into a world capable of long-term biological possibility. Every breath humanity takes is a distant echo of this ancient stabilization when the planet first learned to balance itself within the cosmos. The first minerals and rocks, the chemical foundation of life, begins to form. As Earth cools and stabilizes, the earliest minerals crystallize from molten rock, becoming the planet's first solid memories. These minerals, forged under extreme heat and pressure, mark the transition from a chaotic molten world to one capable of storing chemical information. Among them are zircon crystals, some more than 4 billion years old, holding traces of the planet's earliest conditions. These tiny structures endure through geological eras, offering glimpses into the origins of life. The history of the Earth begins capturing itself in stone. The formation of minerals shapes the texture of the crust. As magma cools, different elements bond together, creating layers of igneous rock that form the backbone of early continents. Granite-like rocks become part of the ancestral cratons, while basalt spreads across volcanic plains and ocean floors. Each mineral type forms under specific temperature and pressure conditions, acting as a geological fingerprint. These fingerprints allow scientists to reconstruct a world long vanished. In their patterns, the planet writes its autobiography. With the appearance of stable minerals, Earth's chemistry becomes increasingly diverse. Quartz, feldspar, olivine, and pyroxene crystallize into distinct forms, each influencing how water interacts with the surface. Some minerals dissolve easily, releasing nutrients into early oceans. Others resist weathering, forming the bedrock of future landscapes. This variety creates new environments that shape early microbial evolution. Minerals become both scaffolding and catalyst for biological possibilities. As rain falls across these primitive rocks, chemical reactions begin carving the planet's first soils. Though nothing like modern soil, these early surfaces hold the ingredients that dissolve into streams and oceans. These dissolved minerals become essential nutrients for ancient microbial life. Weathering processes, powered by wind, water, and temperature, transform the crust into a dynamic participant in Earth's chemistry. Through these exchanges, geology and biology grow inseparable. Hydrothermal systems deepen this connection. Hot water circulating through fractures in the crust reacts with minerals, producing rich chemical gradients that support microbial communities. These systems concentrate metals, sulfur, and other key elements, creating environments where metabolic pathways could evolve and diversify. Life finds refuge in these mineral-rich networks, protected from harsh sunlight and atmospheric instability. In these vents, chemistry learns to imitate the patterns of life. As tectonic plates move, minerals transform under heat and pressure, creating metamorphic rocks that record the planet's internal processes. These rocks lock in information about temperature, stress, and chemical conditions deep within the crust. Through them, Earth's internal dynamics become part of its long-term memory. Each metamorphic layer becomes a silent witness to the planet's restless interior. Through transformation, minerals teach us that change is not destruction, but evolution. The emergence of diverse minerals also influences how sunlight interacts with Earth's surface. Dark volcanic rocks absorb heat, while lighter minerals reflect it, shaping local temperature patterns. These variations contribute to the early development of microclimates, influencing ocean currents and atmospheric flow. Even without continents resembling those of today, the planet begins developing environmental gradients that guide the distribution of life. Mineral diversity becomes environmental diversity. By the end of this phase, Earth possesses a robust mineralogical foundation capable of supporting biological growth for billions of years. Minerals anchor continents, shape oceans, influence climate, and support early ecosystems. They become the silent architects of life, constructing the chemical landscapes where evolution unfolds. In their crystalline structures, the planet's earliest chapters are preserved, and from their stability, the future of life, humanity included, takes root. Preconditions for life. The chemical and environmental stage is set as Earth evolves through the Archean. A unique combination of chemistry, temperature, and stability begins shaping the planet into a cradle for life. The oceans thicken with dissolved minerals, forming a vast chemical reservoir ready for biological innovation. Volcanic gases mix with atmospheric components to create gradients that drive complex reactions. Lightning, ultraviolet radiation, and hydrothermal heat energize molecules scattered across the water. Slowly, the planet shifts from merely being habitable to becoming actively life-generating. Within the oceans, molecules collide, break apart, and reform, taking advantage of the planet's growing chemical diversity. These constant interactions build a foundation of organic compounds, essential for early biology. Amino acids, lipids, and simple carbon structures accumulate in pockets where energy is abundant. Though not yet alive, these molecules mimic some of life's behaviors, assembling into temporary networks. The origin of life begins not with perfection, but with repetition and chance. Hydrothermal vents become some of the most promising environments for early biological chemistry. Their mineral-rich fluids create sharp temperature gradients, offering ideal conditions for molecular organization. Chimneys made of iron and sulfur channel hot water upward, exposing organic molecules to catalytic surfaces. These interactions allow simple structures to form membranes, store energy, and eventually replicate. In these dark environments, life begins learning the rules it will follow for billions of years. The oceans themselves act as protective shields. They block harmful ultraviolet radiation, allowing delicate molecules to accumulate without being destroyed. At the same time, tides stirred by the moon mix these waters, ensuring nutrients spread across vast distances. This constant motion prevents stagnation and increases the likelihood of molecular assembly. Through these cycles, Earth becomes a world where chemistry and motion work in harmony. Temperature stability plays a major role in this transition. As volcanic activity decreases and the climate regulates through ocean-atmosphere feedbacks, surface conditions become less extreme. While still hotter than today, the planet maintains enough predictability to support long-term chemical evolution. In this environment, molecules gain the time needed to interact productively. Stability becomes a silent architect of the future. Minerals also serve as catalysts, trapping molecules in pores and surfaces that help them react more efficiently. Clays, iron-rich structures, and silica networks act like natural laboratories, guiding molecular organization. These mineral surfaces help form primitive membranes capable of separating internal chemistry from the outside world. This separation marks one of the most important steps toward biological structure. Earth's rocks become partners in the rise of life. As these pre-biological systems evolve, energy sources diversify. Sunlight powers reactions near the surface, while chemical gradients feed systems in the deep ocean. Lightning sparks atmospheric chemistry, producing compounds that wash into the sea. Each source contributes differently, creating a planet rich in energetic possibilities. Through variation, Earth achieves the complexity needed for molecular evolution to progress. By the end of this chapter, the planet is no longer a passive geological body, but a chemically vibrant world on the edge of biological emergence. The ingredients for life exist in abundance, driven by heat, water, minerals, and energy. The preconditions for life are fully established, and the first biological structures are ready to appear. In this balance of chaos and order, Earth prepares to take its next great step toward becoming a living planet. Earth's early atmosphere, composition, transitions, and the slow path toward oxygenation. In the early Archean, Earth's atmosphere remains a dense, restless veil shaped by volcanic activity and chemical reactions from the oceans below. Dominated by methane, carbon dioxide, nitrogen, and water vapor, it bears no resemblance to the breathable air humanity depends on today. Instead, it forms a protective but toxic shield that maintains surface temperatures and supports the complex chemistry needed for the origin of life. This atmosphere reflects a planet still learning how to regulate itself. The history of the Earth unfolds through every molecule. Volcanic eruptions release gases that continuously renew and reshape this primitive sky. Plumes rich in sulfur and carbon rise from the mantle, mixing into the lower atmosphere and influencing climate stability. Though chaotic, these cycles create long-term patterns that allow oceans to remain liquid despite a faint young sun. Without these volcanic contributions, early Earth might have frozen entirely. Through fire and gas, the planet maintains the conditions needed for life to emerge. As cyanobacteria begin performing photosynthesis, the atmosphere starts shifting subtly. At first, oxygen produced by these organisms reacts with dissolved iron and other elements in the ocean, preventing it from accumulating in the air. Yet the process continues, slowly altering ocean chemistry and paving the way for atmospheric changes. Oxygen remains a rare trace gas, but its presence marks the first steps toward a dramatic transition. These steps will define future geological eras. Methane plays a powerful role in shaping climate during this time. As a potent greenhouse gas, it traps heat efficiently, preventing global glaciation. However, as cyanobacteria continue expanding, their metabolic byproducts gradually decrease methane concentrations. This reduction begins to cool the planet, hinting at the first major climate shifts tied to biological activity. Earth becomes a world where life and atmosphere interact in increasingly complex ways. The formation of organic hazes adds new layers to the atmospheric story. These hazes scatter sunlight, producing an orange-tinted sky similar to that of Titan today. They influence surface temperature and ultraviolet radiation, providing partial protection for early microbial systems. Yet as oxygen slowly increases in the oceans, the chemistry of hazes evolves, thinning over time. The atmosphere responds to every shift in ocean chemistry, creating a delicate feedback loop between air and water. Thunderstorms and high-energy interactions between sunlight and atmospheric gases help create nitrogen oxides and other compounds critical for early ecosystems. Lightning strikes trigger reactions that form nitrates, which eventually wash into the oceans and fuel microbial processes. In these moments, the atmosphere becomes both a barrier and a supplier, guiding the chemical evolution of life. Through electricity and chemistry, the sky shapes the planet's destiny. The magnetic field also plays a key part in protecting this young atmosphere. Though weaker than today, it shields Earth from solar winds capable of stripping gases into space. Without this protection, the planet could have lost its atmosphere entirely, undermining the evolution of life. Rotation, core dynamics, and magnetic forces combine to preserve the atmosphere as it undergoes slow and profound transitions. Stability emerges from motion deep within the molten core. By the end of this phase, Earth's atmosphere stands on the brink of transformation. Oxygen is poised to rise in what will later be known as the Great Oxidation Event, a shift that will redefine climate, ocean chemistry, and biological evolution. The atmosphere remains harsh by modern standards, yet full of potential for the future. In its layers of gas, Earth carries the memory of its past and the blueprint of everything life will someday become. The expansion of microbial diversity. Evolution begins shaping the early biosphere. As Earth's oceans stabilize and chemical conditions become more predictable, a new chapter of biological creativity unfolds. Microbial life, once limited to a few resilient lineages, begins branching into diverse forms shaped by environmental pressures. Variations in temperature, mineral availability, and chemical gradients guide these early evolutionary steps. Each mutation introduces subtle changes in metabolism and structure. The history of the Earth shifts from chemical possibility to biological exploration. Bacteria spread across the oceans, claiming every niche from volcanic vents to shallow tide-washed shorelines. Some adapt to intense heat, thriving in temperatures that would destroy modern organisms. Others find refuge in cooler, nutrient-rich waters where sunlight filters through. These growing differences lay the groundwork for ecological separation, the starting point for evolution. Through these distinctions, the early biosphere becomes a landscape of tiny pioneers. As cyanobacteria continue to expand, they diversify into species capable of surviving in different light conditions. Some settle in deep layers of microbial mats, while others rise toward brighter waters. These vertical ecosystems create gradients, where each layer specializes in its own function. The interplay between light, chemistry, and metabolism allows more microbial types to coexist. Complexity grows not from size, but from interaction. The emergence of new metabolic strategies begins transforming ocean chemistry. Some microbes learn to use sulfur, methane, or iron as energy sources, broadening the biochemical diversity of early life. These innovations create new chemical feedback loops that influence the entire planet. They affect nutrient availability, atmospheric composition, and even the temperature of the oceans. Life and environment grow increasingly intertwined, shaping each other across vast spans of time. Stromatolite ecosystems become key arenas for this expanding diversity. Layer by layer, microbes deposit minerals and organic material, creating towering structures that evolve over centuries. These formations protect inner layers from harsh ultraviolet radiation, while allowing photosynthesis to continue at the surface. Within these layered communities, cooperation and competition coexist. Stromatolites become early biological cities, each with its own internal dynamics. As evolution accelerates, genetic variation increases within microbial populations. Environmental stress, heat, ultraviolet radiation, chemical changes, forces microorganisms to adapt or perish. Those that survive pass their successful traits to future generations, setting the stage for the earliest evolutionary patterns. These processes unfold without awareness, intention, or complexity, yet they reshape the biosphere. Evolution becomes the silent force guiding Earth toward a future of increasing diversity. Hydrothermal ecosystems continue playing a major role in this biological expansion. Their mineral-rich fluids create chemical gradients that support unique microbial communities with specialized metabolisms. Some microbes extract energy from hydrogen, others from sulfur. These innovations allow life to spread into niches previously uninhabitable. Through this expansion, the biosphere gains resilience, capable of surviving both calm and catastrophe. Diversity becomes strength. By the end of this stage, the early biosphere transforms into a vibrant network of interacting microbial systems. Diversity reaches a level where ecosystems shape each other, forming the first primitive food webs. These webs influence ocean chemistry, atmospheric processes, and the planet's long-term climate. Evolution, once a quiet whisper, becomes the dominant force shaping the future of life. With each new adaptation, Earth inches closer to becoming a biologically rich world. Stromatolites and microbial mats. Earth's earliest ecosystems take shape. As microbial diversity expands across the Archean oceans, certain communities begin forming structures unlike anything seen before. Layer by layer, colonies of cyanobacteria and other microbes trap sediments, secrete minerals, and grow upward toward the sunlight. These formations, known as stromatolites, become Earth's earliest visible ecosystems. Rising from shallow waters like biological monuments, they mark the moment when life begins shaping the planet's geology. The history of the Earth starts leaving physical traces of biology in stone. Stromatolites develop in calm, shallow seas where sunlight penetrates easily and waves remain gentle. Here, microbial mats spread like living carpets across the seafloor. As sediments settle on them, the microbes respond by growing upward to maintain access to light. This repeated cycle builds layered structures that can persist for centuries. Their slow but steady construction mirrors the patient tempo of early evolution. Through them, biology learns to alter landscapes. These structures create complex vertical ecosystems. At the surface, cyanobacteria capture sunlight and perform photosynthesis, producing oxygen and organic matter. Beneath them, deeper layers host microbes that specialize in consumption, decomposition, and chemical transformation. Each layer depends on the one above it, forming one of the earliest ecological networks on the planet. Complexity emerges not from individual organisms, but from community cooperation. The presence of stromatolites influences ocean chemistry. As they perform photosynthesis, they contribute to the slow accumulation of oxygen in the oceans. This oxygen reacts with dissolved iron, creating banded iron formations that settle across the seafloor. These deposits serve as geological records of biological activity, linking the rise of life to the shaping of minerals. The biosphere begins imprinting itself into the planet's geological eras. Microbial mats also stabilize sediments, preventing them from drifting with currents or storms. This stabilization creates microhabitats for other microbes, expanding the diversity of early ecosystems. By slowing sediment movement, these mats influence coastal development and the distribution of nutrients. Over millions of years, they reshape shorelines and shallow marine environments. Life becomes a quiet sculptor of Earth's surface. As these ecosystems expand, stromatolites spread across coastlines around the planet. Their presence signals oceans rich in sunlight, minerals, and stable ecological conditions. They become centers of productivity, converting sunlight into chemical energy that fuels the early biosphere. Their influence extends far beyond their immediate surroundings, affecting nutrient cycles, atmospheric chemistry, and energy flow. Through them, Earth develops its first large-scale biological infrastructure. Though primitive by modern standards, stromatolites represent one of the longest-lasting ecosystems in the history of the Earth. They persist for billions of years, adapting to changing climates, tides, and chemistry. Their resilience reflects the strength of microbial collaboration. Even today, their descendants survive in a few protected coastal environments, offering a living window into the planet's ancient past. In their presence, Earth's story becomes tangible. By the end of this chapter, stromatolites and microbial mats transform early oceans into structured, dynamic ecosystems. They demonstrate that life can shape geology just as geology shapes life. These formations anchor the foundations of biological complexity, paving the way for future evolution. In their layered forms, they hold a timeless message. Life does not need complexity to change a planet. It only needs time, sunlight, and determination. The strengthening of tectonic cycles, Earth becomes a planet of constant renewal. As the Archean world matures, tectonic activity shifts from chaotic pulses to more organized cycles of creation and destruction. The mantle, once violently turbulent, now circulates with deeper consistency, pushing and pulling the early crust in rhythmic patterns. These movements guide the formation of new ocean floors while recycling older ones back into the mantle. Through this process, Earth becomes a planet defined by renewal rather than randomness. The history of the Earth begins to follow geological rhythms. At spreading ridges, molten rock rises from the mantle, forming fresh basaltic crust that stretches across the seafloor. These ridges act like planetary arteries, transporting heat outward and expanding the oceanic plates. As new crust forms, older crust moves outward, eventually meeting zones where subduction pulls it back into the mantle. This dynamic circulation shapes ocean basins, drives volcanic arcs, and influences climate through long-term shifts in heat distribution. Tectonics becomes Earth's internal heartbeat. Subduction zones play a crucial role in deepening the planet's complexity. Here, heavy oceanic plates sink beneath lighter continental fragments, generating intense heat and pressure. These conditions create magma chambers that feed volcanic arcs, releasing gases that affect the early atmosphere. They also produce metamorphic rocks rich in minerals essential for the developing biosphere. In these zones, geology, chemistry, and biology intersect in transformative ways. As tectonic cycles strengthen, continental fragments grow larger and more resilient. Collisions between these fragments build primitive mountain ranges, uplifting minerals that weather into the oceans. This mineral delivery fuels microbial ecosystems, providing nutrients like phosphorus and iron. With each uplift and erosion cycle, Earth refines the chemical distribution needed for life's expansion. Mountains become silent collaborators in the evolution of the early biosphere. The cooling mantle allows tectonic plates to grow thicker, making continental crust more stable through time. This thicker crust resists constant recycling, preserving ancient rocks that carry the signatures of early environments. These preserved regions, known as cratons, become the foundation of future continents. Through preservation, Earth gains memory, geological archives that store evidence of ancient oceans, atmosphere, and life. Stability emerges from deep within the planet. Tectonic motion also influences ocean circulation, shaping temperature gradients and nutrient flow across the planet. When continents shift, they redirect currents, altering climate patterns and microbial habitats. These shifts create new ecological zones, encouraging evolutionary diversity. Through this interplay, tectonics becomes not only a geological force, but a driver of biological opportunity. Earth evolves as a unified system where rock, water, and life influence each other. Volcanism remains a powerful expression of tectonic energy. Eruptions release gases into the atmosphere, contribute minerals to the oceans, and reshape coastlines. While destructive, these eruptions create vast new habitats on land and sea. Lava flows cool into nutrient-rich basalt that eventually weathers into fertile sediment. Life learns to adapt to these cycles, finding resilience in a world defined by constant transformation. The planet becomes a living engine of renewal. By the end of this stage, tectonic cycles have settled into patterns recognizable in modern Earth, spreading ridges, subduction zones, volcanic arcs, and drifting continents. These processes stabilize climate, distribute nutrients, and maintain the dynamic conditions required for evolution. Through tectonics, Earth transforms into a planet capable of sustaining life for billions of years. In its shifting crust, the blueprint of all future ecosystems quietly forms. The gradual buildup toward the Great Oxidation Event, oxygen prepares to reshape the world. As cyanobacteria continue to flourish across Earth's oceans, their collective photosynthesis begins to influence the planet in ways far greater than any single organism could achieve. Oxygen, once an insignificant trace gas, starts accumulating in the oceans faster than chemical sinks can absorb it. Iron, sulfur, and volcanic gases react until their reservoirs become saturated. For the first time, oxygen lingers in the water column. The history of the Earth moves cautiously toward a monumental transformation. This slow buildup shifts ocean chemistry in dramatic ways. Iron, previously dissolved in high concentrations, reacts with oxygen to form rust-like minerals that sink to the seafloor. These deposits become banded iron formations, creating geological archives that span millions of years. As these minerals settle, they remove major oxygen sinks from the ocean. With fewer obstacles, oxygen prepares to rise beyond the water and into the atmosphere. A new atmospheric chapter draws near. Cyanobacterial mats and stromatolite ecosystems amplify this shift. Their rhythmic growth creates vast regions of photosynthetic productivity, converting sunlight into chemical energy with increasing efficiency. Layer by layer, they build oxygen-rich microenvironments within the oceans. Though invisible to the naked eye, these local accumulations redefine global chemistry over time. Biology becomes the architect of planetary transformation. The oceans respond to this chemical shift with changes in habitat distribution. Microbes sensitive to oxygen retreat into deeper, anoxic environments, while newly adapted lineages begin exploiting oxygen-rich zones. This divergence marks the beginning of evolutionary pathways that will someday lead to complex life. Natural selection thrives on change, and oxygen becomes one of the planet's most powerful evolutionary pressures. Life adapts not only to survive, but to diversify. As atmospheric oxygen inches upward, even in trace amounts, it triggers photochemical reactions in the upper atmosphere. These reactions begin forming ozone, a thin shield capable of absorbing harmful ultraviolet radiation. Though still weak, this shield represents a crucial step toward life's expansion beyond sheltered environments. With each incremental increase in oxygen, Earth becomes more hospitable. The cosmos watches as a planet transforms through chemistry alone. Yet this buildup is not without consequences. Methane, a potent greenhouse gas that once dominated the atmosphere, reacts with oxygen and diminishes over time. As methane levels fall, Earth experiences cooling, setting the stage for potential glaciation. These climate shifts expose the deep connection between biology and climate, showing that life can influence planetary temperatures long before complex organisms exist. The environment becomes a dialogue between ocean, atmosphere, and biology. Volcanism continues shaping this transition. Eruptions release gases that temporarily consume oxygen, slowing its rise. But as tectonic cycles stabilize and volcanic intensity decreases, biological oxygen production significantly outpaces chemical consumption. Each photosynthetic cycle contributes more to the planetary reservoir. Through persistence, cyanobacteria prepare the world for an atmospheric revolution that will define future geological eras. By the end of this phase, Earth stands on the threshold of the Great Oxidation Event. Oxygen is no longer a temporary anomaly. It is a force waiting to rewrite climate, atmosphere, and evolution. The biosphere has gained the power to reshape the entire planet, marking one of the most profound turning points in Earth's history. In this quiet buildup, life discovers its ability to transform a world. The transition towards stable continents, the assembly of early land masses. As the Archean progresses, the planet's drifting crustal fragments begin merging into larger, more coherent landmasses. What were once scattered volcanic islands and small proto-continents now collide, weld together, and grow. These collisions release enormous energy, shaping mountain belts and thickening the continental crust. Through these processes, Earth transforms from a world dominated by oceanic crust to one marked by increasingly stable continents. The history of the Earth enters a new stage of geological identity. The assembly of early continents depends heavily on tectonic motion. As mantle convection pushes the plates across the planet, some fragments converge at subduction zones, where oceanic crust sinks beneath continental blocks. This process creates magmatic arcs that add new rock to continental margins. With each eruption and intrusion, continents grow wider and stronger. Geological eras begin to acquire structure through these incremental contributions. As continents stabilize, their thicker crust preserves ancient rocks that record the earliest chapters of the planet's evolution. These preserved regions, known as cratons, become long-lasting anchors for future continental growth. Their roots extend deep into the mantle, making them resistant to tectonic destruction. These cratons form the nuclei of what will eventually become Earth's modern continents. Through their endurance, Earth gains a long-term geological memory. The formation of large landmasses dramatically influences climate and ocean circulation. Continents alter wind patterns, reroute ocean currents, and create new zones of temperature contrast. These shifts affect nutrient distribution and the habitats available to early microbial ecosystems. With more diverse environments, life begins expanding into new ecological niches. Geography becomes a powerful driver of biological opportunity. Continental emergence also alters weathering processes. Rainfall erodes exposed rock, delivering minerals like phosphorus, iron, and silica into the oceans. These nutrients fuel microbial productivity, accelerating photosynthesis and further influencing atmospheric chemistry. Through this cycle, continents become engines of biogeochemical change. The interaction between land and water deepens, weaving biology into the fabric of geology. As continents grow, they experience periods of uplift and erosion that reshape coastlines and river systems. These changes create new sedimentary basins that store chemical and biological information over millions of years. Through these sediments, scientists today reconstruct early climates, ocean chemistry, and microbial evolution. Continents become long-term archives that document the rise of life and the transformation of the atmosphere. Volcanic activity remains active along continental margins, releasing gases that influence developing climate systems. Ash and minerals from eruptions enrich soils and oceans, supporting early ecosystems. Although these eruptions can be disruptive, they also contribute essential ingredients to the planet's evolving environmental cycles. In this balance of creation and destruction, continents become dynamic participants in Earth's development. By the end of this phase, Earth possesses stable continental structures, that will influence the planet for billions of years. These early land masses set the stage for future supercontinents, climate transitions, and evolutionary leaps. They reshape the flow of oceans, the chemistry of the atmosphere, and the habitats available to life. In their formation, Earth declares itself a world not of chaos, but of intricate and enduring design. The Archean world stabilizes. The planet prepares for the rise of oxygen. As continents strengthen and microbial life expands across the oceans, the Archean world enters a phase of profound equilibrium. Earth is no longer a young, chaotic sphere of fire and impacts, but a planet beginning to understand its own rhythm. Oceans circulate in predictable patterns. Tectonic cycles follow consistent pulses, and microbial ecosystems stabilize across shallow seas. Through this balance, the history of the Earth gains continuity. The planet now possesses the foundations required for its next great transformation. The atmosphere remains dominated by methane, nitrogen, and volcanic gases, yet subtle changes ripple through its lower layers. Oxygen produced by cyanobacteria accumulates in pockets within the oceans and along coastal stromatolite fields. Though invisible to the naked eye, these chemical shifts begin influencing the planet's climate. The oceans grow clearer, sediments become more structured, and biological productivity increases. The world prepares itself for an irreversible atmospheric transition. Continental weathering strengthens during this period, delivering essential nutrients into the oceans. Rivers carved by rainfall carry minerals such as phosphorus, iron, and silica to coastal ecosystems. These nutrients feed cyanobacteria and other microbial communities, accelerating photosynthesis and oxygen release. This nutrient flow becomes a self-reinforcing cycle. Continents feed oceans, oceans feed microbes, and microbes reshape the planet. Life and geology collaborate with increasing precision. Tectonic stability creates long-lasting, shallow marine environments ideal for microbial expansion. Sunlight penetrates these waters, energizing vast photosynthetic systems that stretch for kilometers. Stromatolite fields grow thicker and more complex, producing oxygen at unprecedented rates. These ecosystems redefine the early biosphere, setting the stage for biological revolutions still millions of years away. The oceans become Earth's largest engine of planetary change. As the mantle cools further, volcanic outgassing decreases gradually, reducing the supply of gases that once consumed oxygen. With fewer chemical sinks available, oxygen begins lingering longer in the oceans. This shift marks the first true precursor to the Great Oxidation event. The planet transitions from resisting oxygen to allowing its presence. Chemistry is no longer dominated solely by geology, but increasingly by biology. Climate patterns adjust to these slow atmospheric changes. Methane concentrations start to fluctuate as oxygen interferes with its stability. These fluctuations create temperature variations that influence ocean currents, glaciation potential, and microbial distribution. While the planet remains warm enough to avoid global freezing, the first hints of long-term climate vulnerability appear. Life, geology, and atmosphere begin shaping each other's limits. The magnetic field stabilizes further as the core continues cooling at a steady pace. This stable field protects the atmosphere from solar winds, preventing major atmospheric loss. Without this shield, oxygen could not accumulate during the coming eras. Rotation, magnetism, and internal heat work together to maintain a planet capable of transformation. Earth becomes increasingly resilient against cosmic forces. By the end of the Archean, Earth emerges as a fully self-regulating world with interconnected systems of rock, water, atmosphere, and life. The planet stands at the doorway of one of the most dramatic events in its geological history, the rise of free oxygen. From this stability will come both crisis and opportunity, extinction and evolution. In this moment of quiet balance, Earth gathers the strength it needs to become the oxygen-rich world humanity will someday call home. The Archean teaches us something profound. Even in a world shaped by fire, darkness, and uncertainty, the foundations of life can emerge. Every mineral, every ocean, every microbial bloom was a reminder that transformation begins quietly, long before anyone can see its future. When we study the history of the Earth, we discover that stability is not born from perfection, but from persistence across geological eras. This lesson is not just scientific, It is deeply human. Carry this understanding with you. Let the patience of early oceans and the resilience of ancient bacteria challenge how you face your own challenges. The planet's earliest chapters reveal that even the smallest forces, repeated over time, can reshape a world. Ask yourself, how can you apply this truth in your own life? Where is your own Archean, your moment of raw potential, waiting to evolve? Now I want to hear from you. Which part of this journey surprised you the most? Do you believe life elsewhere in the universe follows similar paths, or is Earth a rare exception? Your reflections help us explore the cosmos together. And if this journey spoke to you, make sure you subscribe to Chronicles of Earth, activate notifications, and join a community that explores the universe with curiosity and purpose. Every video expands our understanding of life, the planet and the cosmos we belong to. Before we close, I leave you with the words of Carl Sagan, who dedicated his life to revealing our cosmic roots. We are a way for the universe to know itself. The Archean is the beginning of that knowing.